Hello, and welcome back to our discussion on uncertainty in stage-discharge relationships. We will now discuss uncertainty in observed data at stream gauge locations. A stream gauge location is based on the selection of a site by the USGS to perform the collection of observed data on a river. The rating is constructed based on a collection of observed water surfaces and velocity measurements for a given cross-section during a flow event. To construct an accurate rating, you must have enough measurements to characterize the range of flows. However, there is measurement uncertainty both with the measuring device, reading the device, and the possibility that the cross-section shape is changing during the flow event. Further, the shape of the hydrograph and response of the river system can influence the resulting rating. The effect of the river system in concert with the hydrograph shape on the results of the rating curve results in what we call a looped hydrograph. We'll talk about that in a minute. Let's take a look at how the event is actually recorded. So if I'm out on a river and I'm observing flows coming down the river, I'm going to measure stages. The measured stage velocity measurements are then used to compute a flow. This will occur for several stages during the flow event. Then, after I've seen numerous flow events, I will have numerous points from which I can build a rating. However, you can see a scatter in the data points. This is often due to the shape of the hydrograph and the response to the river system to it. So if we look at a particular stage, the computed flow that we have may be much higher at this location or for this measurement than for this other measurement that's showing lower flow. This could be due to the fact simply that on the rising side of the hydrograph, the flow downstream is low, so we're not having backwater effects. So for the same stage, we have a lot of flow, whereas on the falling side of the hydrograph, as denoted by this point, we have less flow because the downstream water surface elevation is higher than it was during the rising portion of the hydrograph, thus reducing the amount of flow we can get through the cross-section for the same stage. Once we have developed our rating then, we can come up with a mean rating curve for all the observed flow events. This mean rating curve is what we refer to as the rating curve. But despite us having this mean rating curve, you can see there's quite a bit of uncertainty about that relationship. Let's take a look at this then when we go to use that rating curve for an observed event. A future event comes along and we have already established our rating curve for the system. As that flow event occurs along the river, we go to the gauge station and we can record stages. If we take a particular stage then for that event, we can go to the mean rating curve and get a flow. However, associated with that stage is quite a bit of uncertainty about what the flow should actually be, as we can see by light red bars in the graph. That uncertainty in our rating curve we can try and capture. To capture the uncertainty in the stream gauge location, we can do direct analysis of the observed data that went into making the rating curve. Uncertainty in those points in the rating curve can be due to the following: changes in the cross-section shape during the flow event, changes in surface roughness or Manning's end values that are used in Manning's equation to compute flow, measurement error, either in the device or how the user interprets the device, the influence of backwater from downstream, and other factors we talked about, like a loop in the rating curve. To then compute the uncertainty in that rating curve, we can compute the standard deviation as our estimate for the uncertainty. The standard deviation is computed as a square root of the sum of the squares in the difference between the observed and the measured rating data. When we go to compute stage uncertainty, we like to compute this uncertainty at various water surface elevations or flows. In the figure shown on your screen, you can see that we have 3 different flow zones. We have a low flow zone where the river is contained within the river banks. We have a higher flow zone where water is getting out into the floodplain. And then we have the area of extreme flood events. Now, typically, our uncertainty is very low as we are near zero. With zero flow, we have zero uncertainty. As we get a little bit of flow in the channel, we have a pretty good idea where it's going to be, as you can see by the data points following the rating curve. As flow starts to go out of bank, uncertainty in the rating curve may become more uncertain, or it may stay relatively certain depending on what the floodplain in the overbanks looks like. If the floodplain is wide and flat, then large changes in flow may not affect the stage very much at all. However, we tend to see increases in uncertainty as we get into high flow, extremely high flows and rare events. This is due to conditions where we don't know how the floodplain is going to react to these events because we do not experience rare events as frequently. We don't know how the floodplain is going to react, and we have less observed data to go by. In the next presentation, we'll discuss uncertainty in computed water surface profiles.